For a second order system with a step input, we know that the general solution depends upon the value of the damping ratio. And we also have seen that the response is the combination of the homogeneous solution, which in dynamic systems we're going to call the free response, and the particular solution, which we're going to call the forced response of the system. So depending upon the value of the damping ratio, we see that the free response, the form of the free response, is going to depend upon the value of the damping ratio. And from our studies of the free response cases, or zero input forcing function, we know that we have our overdamped case, which is going to slowly approach the zero steady state value. We have a critically damped case, which is going to quickly approach the steady state value without overshoot. And then we have the underdamped case, which is going to give us oscillations about the final steady state value. If we have a step input, we also know that the forced response is given by the value of the constant forcing function that's applied after time is equal to 0 divided by the stiffness of the system. So for a step input, we have these, depending upon the damping ratio, we have three possible values or three possible expressions for the free response. But the forced response is always going to be f over k. And if we look at what happens mathematically in all of these cases, as time gets really large, since in most of the cases the eigenvalues are going to be negative values, these exponential terms are going to decrease. The effect of those exponential terms is going to go away. So after a very long period of time, the only thing that's going to be left of our step input response is our forced response, or our particular solution. So that tells us that in addition to being the particular response, or the particular solution, the forced response is also what happens to the system in steady state for a long time after the step input has occurred. So recall that all of these functions, or all of these formulations, are valid only for time greater than 0. And the particular solution is, since it's just a constant, as time goes towards infinity, it's going to remain the same value, f over k. Therefore, we call this solution the steady state response. All right, so this is also the steady state response of the system. Now you can see that there's really no differentiation between a step input and a free response case. The only thing that's different here is that we have this steady state, we have a different steady state value about which the second order system is going to settle. So really the formulation is exactly the same for both of them. The free response case occurs when f has a value of 0, and the step input case occurs when the f is a non-zero value. So therefore the expected behavior of these second order systems is going to look a lot like the homogeneous or the free responses that we've looked at previously. So if we take a look at the response, the general characteristics of the second order system responses, here we have a system that has very similar parameters, at least the same stiffness value or the same k value associated with it, but we have different ratios of the inertia term and the damping term. We have three different cases. We have a overdamped, a critically damped, and an underdamped system. And we see that in all of these cases, the system starts at some initial value. It may or may not be 0, depending upon what the initial conditions of the system are. And then depending upon the damping ratio, the response is going to approach the steady state value, this f over k value, in a couple of different ways. If we have an overdamped system, it's going to slowly approach the final steady state value. If we have a critically damped system, it's going to quickly approach the steady state value without having any oscillations or overshoots. It's not going to go above or below the steady state value. And then of course when we have an underdamped system, we're going to get oscillations about the steady state value, that F over K value. This response is almost identical to the free response case where we had a zero forcing function on the right hand side of our differential equation. If you recall, the responses looked identical to this, with the only exception being that the final steady state value, because we weren't adding any energy to the system, was going to settle out to a value of 0 instead of some non-zero value.